And now I'm pleased to welcome Dr. Tibor Herman and Mr. Péter Püspöki, two representatives of a four-member satellite development team with an extensive academic heritage, developers of 𝗚𝗚𝗺 or 𝗗𝗄𝗺, the first Hungarian satellite in orbit, and of 𝗚𝗘𝗺, the 100th PocketQube launched to space. Together with Genesis, they are now developing the 𝗗𝗲𝗺𝗺, a picosatellite that hosts the 𝗗𝗲 capsules and is deployable via standard PocketQube dispensers, making microgravity research truly accessible. Pay close attention, then what is about to happen is very special. They will power on the 𝗗𝗲𝗺 spacecraft for the first time in front of public and attempt to transmit live telemetry directly from the satellite. This moment also marks a historic milestone, as 𝗗𝗲𝗺 is most likely the smallest re-entry vehicle ever to fly to space. And I would like to welcome Dr. Tibor Herman and Mr. Péter Püspöki for the presentation.
So, welcome everyone. My name is Tibor Herman, and we come from TU Budapest, or BME, Technical University of Budapest, and we are part of the radio club of the university, which is the contractor for Genesis for this 𝗗𝗺𝗺𝗺 PocketQube. So, as a beginning, I would like to start with our flight heritage. With our PocketQubes and the CubeSat satellite. So our first satellite ever in Hungary was 𝗗𝗄𝗺-1, which was a one-unit CubeSat satellite, same size as 𝗗𝗄𝗺-1, which you can see here in the display case. And then we moved on to a smaller satellite platform or standard, which is called PocketQube. It is called PocketQube because it fits in your pocket. The base size of 1P satellite is just 5 by 5 by 5 centimeters. We usually like to refer to it as it's the size of a Rubik's Cube, which is a Hungarian invention. So our first PocketQube ever at the university was 𝗚𝗃-P, which has a twin brother, 𝗚𝗃-1. Both are a 1P picosatellite measuring human-caused electromagnetic pollution in space from low Earth orbit. The aim was to measure or analyze the DVB-T, the terrestrial video broadcast band, between 400 and 800 megahertz. And later on, you will see the research results from this measurement or this mission. Our second PocketQube satellite was 𝗚𝗃𝗺-1, which was Hungary's first private satellite. It was a 2P PocketQube with 4 different kinds of thermal insulation materials around 4 different batteries or 4 identical batteries. And it also had the same mission as 𝗚𝗃-P and 𝗚𝗃-1, so it also measured electromagnetic pollution from space. Then came MRC-100, which was a 3P PocketQube. We moved on to a slightly larger satellite, which was a collective of different experiments in space. And I would like to emphasize that all of these satellites are built by students and lecturers at the university. And so it is built into the educational system. So students can get first hands-on experience firsthand in building, operating a satellite, designing, building, and operating a satellite. This small form factor allows a cheap, very cheap access to space, and this also democratizes the access to space technology and space research. So all of these missions were successful. The first 2 satellites, 𝗚𝗃-P and 𝗚𝗃𝗺-1, operated for 10 months, around 10 months. And then MRC-100 𝗚𝗃-1 spent more than 3 years in orbit. But of course, as a small satellite, it doesn't have the capabilities to operate as long as a larger satellite, which has more protection against the harsh environments in space. I'm mostly saying this against radiation. So 𝗚𝗏𝗺𝗎 was also a successful mission. It operated for more than 1.5 years, and it re-entered Earth atmosphere this January. Okay, so here's a mission overview for 𝗚𝗏𝗺𝗎 and 𝗚𝗏𝗺1, calling them smoke satellites together. As I said, it measured electromagnetic pollution from space in a 1P form factor. It is resilient to the extreme temperature environment found in space. So it operates from -40 up to +80 degrees Celsius. And I would like to connect here to Max that he's trying to lower the temperature as much as possible so that the electronics can survive in space. So all of these satellites are single point of failure tolerant satellites, meaning that if anything goes wrong, let's say a component fails or a semiconductor fails, we can still switch over to the spare module on the satellite. Yes, it is also validated for the rocket's vibration requirements, which was a qualification value is 20G, and the acceptance level is 5G of vibration, a random vibration during launch. That is expected during every launch of a satellite. So the two launches were, sorry, I'm shading it out. So we had two launches for these two satellites in 2019 and 2021. And as I said, one mission took 10 months and the other one 3 years. So I would like to skip straight into the mission results. So with these satellites, we were able to create the world's first electromagnetic pollution map in the DVB-T band, in UHF band, where you can see that we can actually measure what is radiated into space. We are talking about high-power broadcast stations transmitting around 1 kilowatts of power, which can penetrate the Earth's atmosphere and can get out to space. The problem here is that it will increase the noise level even in the satellite communication frequency bands. So that is why this research was important, because it's basically noise. It will increase the noise floor for satellites. So the transmitting stations from Earth will need to transmit with higher power to reach, to establish the connection with their satellites. So 𝗚𝗏𝗺𝗎 included many experiments. I don't want to list them all. You will see a list on the next slide, but here are some main facts of this satellite. So it's a 50 by 50 by 178 millimeter chassis, and it was covered with solar panels and powered by solar panels. It included 2 batteries, and it had almost the same requirements as 𝗚𝗏𝗺𝗎 and 𝗚𝗏𝗺1 in terms of environmental testing. It was launched in 2023 June, and as I said, it included many experiments, not just from TU Budapest, but from other universities in Hungary. And here you can see not the exploded version of the satellite, but the naked version of the assembly. And here's the list of all the different experiments that we had on board. The most notable ones are the attitude determination and control system, S-band downlink for high data rate telemetry transmission, and file downloads. We also had a sun and horizon sensor on board, and apart from the base subsystems. Again, this was also a redundant satellite, so the basic subsystems had their spare models in case of a failure. And here's a nice video from space. We took a sequence of images, which we then downloaded, and we could make a short video of it. On the top right corner, you can see the actual antenna of the satellite, and as it rotates, you can see the shimmering of sun. So our latest satellite is Unity. The name stands for Hungarian University and Unity, meaning that the satellite first primary payload is 1 unit or a 1P PocketQube, which was developed by 𝗚𝗘𝗏 University. And the rest of the payloads are actually developed by high school students from Hungary who were the finalists of 2024 CANSAT competition in our country. So there were 6 high school teams who had the chance to build their own experiments. And on the top board here, you can see 5 of them. And if we deploy this PCB on the other side, there are other, the rest of the experiments can be found there. So there are a couple of new inventions for us in this satellite. First thing to notice is that it has deployable solar wings, apart from the deployable experimental panel. And it was covered with many more solar panels than 𝗚𝗏𝗺𝗫 or the SMOK satellites. So it had much better power budget for energy management. The main goal of this satellite, apart from these payloads, is a technological demonstration, and we would like to test our platform, the basic subsystems of this satellite, because we would like to commercialize the platform itself, which will be useful not only in this satellite, but also on Gen 1P. And we had 2 types of attitude determination control system or attitude control system. One is magnetic, the same as in 𝗚𝗏𝗺𝗏, and the other one is a rotated mass, based on a rotated mass principle. As I said, 2 payloads, the university from 𝗗𝗲𝗺 and the high school students, and the launch is actually in 55 minutes. So Transporter 15 mission will launch actually in 55 minutes. It has been postponed several times. I think this is the 4th time it has been postponed in the last 2 weeks. And hopefully tonight we will have a successful launch of this satellite. Why am I telling you all of this? This has been our flight heritage, and Gen 1P will build on this flight heritage, on the experience that we've gathered throughout the last more than almost 10 years. And from now on, I would like to give the word to Peter, who will speak about or talk about Gen 1P's host satellite.
Thank you, and I would like to also welcome everyone here. So, as Tibor said, we have a quite extensive experience already in developing PocketQube satellites, which was really important because we had a very short period of time to develop the Gen 1P satellites. So here you can see the main components of this satellite. So the base of the satellite is built on the previous platform we have developed. It has very similar components. The power system is utilizing the same components we already used. The communication model is almost identical to the one we had in our previous satellite. It had to be changed slightly to fit the purpose of this one. So this is a really important part in speeding up the development process and making it more as easy to reproduce for multiple satellites, to reuse most of the components. And In the capsule, we will use the same communication module that's in the satellite. And besides that will be a GPS module, the parachute system, and the battery, and of course the experiment. So here you can see the open solar panels of the satellite. After the presentation, you're welcome to take a look at this in real. And we already have some of the, we already have the first version of this satellite built, and that's the one we can present to you tonight. And here you can see just the PCBs of the satellite with the first version of the capsule inside. So these are the main steps of the mission. First, when the satellite is finished, it will be placed inside the deployment pod that is developed by 𝗗𝗏𝗺𝗐, a Scottish company. Then it will be launched to space next year. And once it's in orbit, it will wait for the sunlight. And when it charges its batteries and it has enough power, it will open the communication antennas and the solar panels. Then we can establish the connection with the satellite, between the satellite and our ground station. Then we will have to wait until its orbit is decaying, and just before the re-entry, we will separate the capsule. The satellite part will burn up in the atmosphere, but the capsule, with its protection, will survive the re-entry, and it also has the communication module inside, so it will transmit the GPS data and location when it's about to land, and that's how we will be able to find it. And then Tibor will talk a bit about the mission timeline.
Okay, so for the mission timeline, we have started this whole project in early September, and we had some meeting negotiations regarding the design itself. It took almost a complete month, and then throughout October and November, we conducted the design phase of the whole satellite. Later on, there will be extra design time for the capsule electronics as well. And then, as we are integrating the satellite, we will also conduct functional tests. And at the end of the testing phase, we will perform environmental testing and long-term testing as well to make sure that the satellite operates as intended, not just in the lab, but also in space. This will be conducted around late February as of now. But as I've said just now, that these launches tend to be postponed either by days or it could be weeks or months even. The launch itself might be postponed here as well. But as of now, we are targeting a March launch. So this timeline has been designed to accommodate this timing. So regarding the presentation, this was the visual part, and I would like now to demonstrate the operation of the engineering model that we've just brought. And I'd like to ask for your patience while I power up my system to do that. Great. Okay, so what you can see here, I'm sorry if, okay, there's a noise from my computer, but already on this waterfall diagram, you can see the received signal from the Gen 1P engineering model, which is back there in the clear display. and we can hear some packets transmitted from there. And on the right-hand side in this terminal, you can see that the actual telemetry data coming from the communication module of this satellite. So this is what the actual operation of the satellite will look like. We will receive automatic telemetry data from the satellite, and we will see the health status of the different subsystems. We can also download images from the satellite, because there's a camera, a selfie camera on board, which is a good visual feedback for the deployment of the capsule. As I said, this is just a demonstration purposes, so it's a reduced set of telemetry data, but on the live satellite from space, there will be much more data. As soon as the capsule is detached and as it starts to descend, during the descent, we will use a different frequency band from the one that we use here. So this communication scheme is a relatively high-speed data downlink, but since during descent we will not be aware of the actual position of the satellite until the parachute is deployed, we will have to use a different kind of communication protocol, which is called LoRa, which stands for long-range communication. It's a very robust and really long-range communication scheme. The drawback is that the data rate is very small, so we will have to reduce the amount of data that we transmit. So this data will be reduced to basically an identification and the location of the re-entry capsule. And hopefully, with a set of ground stations, or at least one ground station from here on Earth, we will be able to locate the descending or the re-entry capsule when it arrives to Earth. And I think that concludes our presentation. And please feel free to ask us any questions during the questions phase. Thank you.